Hello everybody and welcome back to another video. After having seen what a vacuum technology is and how we make the vacuum, we will see one of the application, which is the atomic force microscopy. Of course, this video is going to be just an introduction to the broad topic. AFM is quite recently technique, maybe started in 1986 or so. And the purpose of this method is to measure the sample topography by means of an elastic cantilever, which we can think about a cantilever beam, which features a tip. Okay, just to give you some idea, this cantilever length will be something about 100 microns or so, whereas the height of this tip is approximately, let's say, the order of 10 micron. Okay, so this tip is made of silicon and as well as the cantilever, and when it is brought in close to the contact with a sample, it will start to bend. The sample itself is resting, let's say, on a piezoelectric equipment. So we have our samples here, which is this yellow one, and the cantilever, which is connected, may be connected to a driver, but we will see later on. So let's say for the time being that is connected somehow, will be brought closer to the contact with the sample. This is the sample. And because of the interaction that there is between the tip and the sample, we will observe a bending of the cantilever. So the cantilever will actually bend toward the sample if we are in a certain regime. It will be experience a repulsive forces if it's too close, but we will see this later on. What is important what is important now for us is that there is a laser beam, okay, which is pointing directly on top of the cantilever, and the laser beam will be deflected if the cantilever is bending, okay. It will be deflected by a certain angle, and it will be hitting a detector, a photodiode detector, which is this one, okay. And according to the curvature of such cantilever, the bending on the cantilever, we can determine if there has been displacement in one direction, lateral displacement, because of course you need to think about that the cantilever itself, the tip itself, is made by atoms, and these atoms will interact with the atoms of the surface of the sample. But this is not a flat surface; you're gonna have some topography. Therefore, we might have lateral forces as well as vertical forces. So, just to give you an idea of the photodiode, will be something like this. We will have 4 quadrants. Okay, let's call this first, second, third, fourth quadrant. And the laser beam will be effectively like, say, an ellipse, okay, which is maybe moving up and down. Okay, so if we want to measure, let's say, in the z direction, we will have to do the delta I first plus delta I of the fourth quadrant minus the delta I of the second plus the delta I of the third, just to give an idea of how we can effectively measure this deflection in the z direction. Okay, so the laser may be pointing here, or maybe like this, with predominantly in the first and the fourth quadrant rather than the second and the third. And the same goes for the lateral resolution. We may have something like that, where the laser is pointing partially on one, partially on the other. So we will define a lateral as the delta I of the left, which is 4 plus 3, minus the delta, the sum of the deltas of the right side. So first plus delta I second. Okay, so before going into the details of the interaction between the tip and the sample, which, as I anticipated, there are three regimes. If the tip is far away, there is no forces and the cantilever is essentially unbent. When we bring it closer to the sample, we will see a bending, and the bending is going to be towards the sample. And as soon as we reach a closer distance from the sample, we will the cantilever will experience a repulsive forces. Okay, and we will see this in a second. But in this video, I would like to start focusing on the mechanical stresses and strains that a cantilever will experience. Okay, because this is the starting point before even discussing what will be the types of mode, which is contact mode, static mode, dynamic mode, in which we make the cantilever vibrating, deliberately vibrating at a certain frequency. But none of this will be seen here. We will focus on the mechanical behavior first, and once we have understand that, we will move on other topics. Okay. So how do we start this? We started by making a better picture, which is generally a very good idea in general. Okay, so let me sketch it, the cantilever like this. Okay, it has this tip. Okay, let's put some coordinates. So this can be, maybe it's better to do it dotted. Okay, even black is fine. Okay. All right, so we get this is y, x, and z axle. This is the cantilever, which is fixed in one part. Okay, the cantilever has a certain length, as we have seen. We denoted this length by L. It has a certain thickness, which we denote by T, and it has a certain width, which we can, the picture is W. Okay, so width, thickness, and length. And of course, this is the length of the cantilever, which we denote by L tip. Of the tip, sorry, not of the cantilever. And okay, so what would be the displacement and the forces relation in this case? Well, it's actually following the Hooke's law, okay, in which I hope everybody is familiar with, which is this type of law. The force is proportional to the displacement, and the proportionality is called stiffness, which we denote by K. And actually we are rather more interested in the displacement, so we need to reverse this equation, have x equal to k to the minus 1 f, okay, where k to the minus 1 is the inverse of the stiffness. But we have three directions here. We have x, y, and z. Therefore, we will need to consider, starting from this monodimensional equation, an equation which consider all three directions. So allow me to write it in terms of a tensor. Okay, so we have our displacement vector, delta x, delta y, delta z, a tensor which is the inverse of the stiffness tensor, which has 9 components: cxx, cxy, cxz. Then we have cyx, cyy, cyz, czx, czy, czz. Okay, and the three forces vector, f of x, f of y, f of z. If we are able to compute all these 9 coefficients, knowing the forces, we will be able to estimate, to calculate precisely the displacement into the delta x, delta y, delta z direction. So our purpose here is to construct such inverse stiffness tensor, the components of such tensor, and we will need to do it step by step. So considering first one forces, then the others. So let's begin our discussion by considering a forces. Let me see if I can take everything. Okay, this I don't need. Okay, so let's start the first part in which we apply a forces into the z direction, f of z. So this force will essentially bend the cantilever . It will bend the cantilever . Okay, in this way. And also the tip will bend. Okay, because of the effect of this vertical force, f of z. So we want to study the displacement, which are the delta. Let's say, if it's f of z, one can think about that the deformation will be only in the delta y and delta z direction and none in the delta x direction, okay? Because the tip stays in the plane depicted by y and z axle. And this is correct in the sense that we will have, we can think about delta x equal to 0 if there is only vertical forces, which is true. So we will have, what we want to measure is this delta z, distance between this and this, and of course also the delta y, which is the projection in this way, delta y. Okay, so this is it. Now let's say in terms of equation where we have a delta x, delta y, delta z, we have the same matrix here, but okay, but the f of x is equal to 0 and f of y is equal to 0, all right? So if we do the multiplication, we will see that when we do the matrix multiplication, we have that the only column that survive is this one, okay? Because the other will multiply 0, so they cancel out. Therefore, the set of equation that we need is delta x is cx of z f of z, delta y is cy z f of z, and delta z is equal to czz f of z. Okay, so we have seen that this one is equal to 0 immediately because the displacement occurs only in the yz plane and nothing in the x plane, so this is immediately solved. So our task here is to solve these other two equations, okay? And to do so, we need to begin with some consideration on the strain and the stresses. We need to take an element, okay, which has a length L. It has a neutral axis. What is a neutral axis? It is an axis in which the stress and the strain is equal to 0. So there is no strain. And when we bend this, okay, we see that crosses the neutral axis. And the bending of this element, okay, will identify two regions. One region in which there is a compression, which is this one, and the region in which there is a elongation, let's say a deformation, a tensile deformation, and the neutral axis stays there. So we can identify a curvature, okay, so this lower part as we need to insert a certain variable, which we call z, and there is also a radius of curvature, okay, of this element, which is somewhere in the upper or the center of this radius of curvature. So we have, this is our delta L. Okay, so we notice that the more delta L increases, and there is a directional proportionality with the Z. Okay, the more Z increases, the more delta L increases, right? Which is the correlation between these two variables. If we make this proportion, delta L is divided by Z over R, we have what we need for the later discussion. Okay, this is the proportional, is given by inspection of the proportionality of this element of length L, this deformed by a delta L. Okay, so what else do we need to consider? We need to consider that because of these forces, F of Z, there is also a moment, a bending moment, and the bending moment can be, think about the integral of elementary force dF times Z, no? This is the bending that we have. What we need from here is to define this dF, this element of the forces, and to do so, again, we need the Hooke's law in a more general way. The Hooke's law, the generalized Hooke's law, is that the strain, okay, which is, the strain tensor, which is this one, is proportional, the stress tensor, which is this one, excuse me, stress tensor is proportional to the strain tensor and the proportionality is this 4-rank tensor here, E, which sometimes called Young's modulus in monodimension. But what is the strain? The strain is if we go from tensor description into an infinitesimal description, we know that the strain is dF over ds, so it's a force, elementary forces applied on an elementary surface. So we have our ds, okay, whichever shape, and the d of f. Okay, so this creates stresses which we can think about as a distribution of smaller forces, a pressure, okay, as to say. So this sigma is dF over ds into an infinitesimal view. E is the Young modulus, okay? And the strain tensor in the infinitesimal picture we can think about as delta L over L. So it's the proportionality between our delta L and the length which started off. So this is there is no dimension for strain, it's just a dimensional physical quantity. So from this we can see that if we make use of this equation here, we replace delta L over L with Z over R. So we get E Z over R, okay? And from this we obtain that dF is E Z over R ds. We substitute this dF into here in our equation of momentum. So we have that this is the integral of what? Of dF, which we said is E over R Z, but there is already a Z, so it's Z square ds, okay? We can take out the constants which do not depend on the integration measure, ds, so it's E over R, and this is the integral of Z square ds. But what is this? This is an inertia moment because it's an area multiplied by a distance squared, so it's an inertia moment, which in a certain sense it describes us how the mass is distributed around the center of the mass. And for a specific cross-section, like in our case of the cantilever, where we have, imagine to take a cross-section here, for example. Okay, so if we take such a cross-section, we will have, let's make it a little bit bigger, so it will be something like that. This is a cross-section of our cantilever, okay, which has, as I anticipated, the thickness T and the width W, okay, W. So the inertia moment, Z, which is the integral Z square ds, it's for a shape, a rectangular shape like this, it's equivalent to 1 over 12. The base, which is W, and the thickness to the cube. Okay, so this is the inertia moment for this cross-section. If we have a different cross-section, we will have a different inertia moment. If we have a square, it will be something proportional to pi divided by 32. diameter to the cube or something like that. Okay, so dimensionally is a length to the fourth, so we need to keep in mind that. Okay, so let's go on. We simplify that. We associate to that integral this inertial moment. So we have m is equal to ejz divided by r, the curvature, the radius of curvature. By the way, this appears to the product of ejz is the bending stiffness. What is called in bending stiffness, and 1 over r is the curvature. So if we reverse this equation, we obtain that 1 over r is equal to m over ejz. Okay, but 1 over r, okay, if we introduce here a quantity, a function, which we could call u of y, okay, and this function measure the displacement towards the z-axis as the y varies. So y is the length of the cantilever. So for example, if we say u at y equal to L, we are measuring the displacement here, our delta z. Introducing this function, we know that the curvature, so this 1 over r, is proportional to the second derivative of this function, is equivalent to the second derivative of this function with respect of y. Okay, let me write it a little bit more clearer. The second derivative of this function u of y, which is is called the curvature, is proportional to the moment and inversely proportional to the static stiffness, the bending stiffness, sorry, ejz. Now, in order to obtain what we need, which I would like to recall is this coefficient here. This is our goal. In order to get that, we need something that we need to some equation which allows us to get delta z as a function of delta f. Okay, so right now we have a differential equation which we can integrate, okay, to get solution. But before doing so, we need to specialize that this m momentum, in the case of f of z, is f of z times what in the coordinate system that we have chosen is L minus y. F of z L minus y, force times distance. Okay, and make ejz. So we integrated this and we get f of z divided by ejz, and we have ly minus y squared over 2, and if we integrate again, f of y, u of y is f of z ejz ly squared over 2 minus y to the cube 6. Now if we replace, instead of u of y, u of L, we get our delta z, which we want, which is f of z divided by ejz. This is L to the cube divided by 2 minus L to the cube divided by 6. But L to the cube divided by 2, we can think about 3L to the cube divided by 6 minus L to the cube divided by 6. So it's 2. So it's 2 minus 1 is 1/3. Yes, because it's 3 minus 1, 2, 2, 1/3. Uh, 3 minus 1 is 2/6. 1/3, yes. L to the cube. So if we rearrange this, we get the delta x, delta z, excuse me, is equal to L to the cube divided by 3 ejz f of z. But this is exactly the equation that we are looking for, which is this one. It has the same form. We have delta z, czz, and f of z. So it appears that czz is this quantity here. Okay. We also denote this as c, little c. So let me write in here, c is equal to L to the cube 3ejz, which will be used later on because we want to normalize everything according to this little c. All right. Okay, so we get the first coefficient. Let's move on the second one, which is delta y. Now we need to solve this equation, delta y. And delta y, we observe that it's somehow proportional to the length of the tip. In particular, if we think that there is a rotation angle between these two. I don't want to spoil too much this drawing. I don't know how to do it, but essentially if there is an angle between this quantity, and this angle is called alpha. So it means that this alpha, L to the tip alpha, is our delta y, okay? But what is alpha? Alpha, we can think about using this equation, because effectively this is du over dy, and it appears that is exactly the alpha that we are looking for. So if we make use of this equation, which I let me copy it down here for convenience. Okay, and we specialize it into y equal to L, so u prime of L, and this is f of z divided by ejz. Ly, so this is L squared minus, let's say, L squared divided by 2. So it's 1/2 L squared divided by ejz f of z. Okay, we insert this into the delta y. Delta y is equal to L tip, which multiplies this alpha, but alpha is this one. So what we get L squared divided by 2 ejz f of z. But what is f? Okay, f f of z is this one. Okay, L to the cube 3 ejz, so we need to normalize it according to our C that we discussed above. So how do we do it? We need to imagine how to make use of this equation here. So to do so, we can do in this way. We can see that there is L squared divided by ejz, which we can think we have C L, let's do it this way. I divide by L, so this is, I put the 3 here, we have ejz. So I just rearrange the terms of the C, because I can see now that this is what I want to replace inside, because I want to have it in terms of C, that's why. So it's L of the tip divided by 2, and I insert 3 C over L f of z, yes. So let me rearrange this. We have delta y is equal to 3 over 2 L tip divided by L C f of z. And this is our C y z coefficient, okay? So if we pick our bigger matrix here, this one, and we copy it down here. After all this calculation, we have obtained CZZ, which is C, this quantity here, L to the cube divided 3 ejz. And what else? And we have this other, no, not yet. Well, actually, this one are 0. This one is 0. And we get this one, which is L tip divided by L 3 over 2 C. Okay? And we still need the other components. So for the other components, we need to restart from the beginning. Let me take the preliminary drawing, this one, but I want it with all the coordinates. Okay, copy. Let's go down. Okay, this is it. This is, we don't need. What do we need? We also need the this equation. Okay, here. Now, we have finished one column. Let's start with the other one. Let's consider f of y in this case instead of f of z. So the other are 0, which means that we are extracting this column here, okay, by doing the matrix multiplication, which is delta x, delta y, and delta z, which is equal to, let's put it directly into an equation form. So it's cxy f of y, cyy f of y, and czy f of y. Okay, so this is what we need. and the force is into the y direction. So this is our f of y, which will cause again a deformation of the cantilever and of the tip, which essentially is like a bending. And again, we have delta y and delta z. We have a delta z and delta y displacement, which we want to measure. And again, no delta x direction. So because this again occurs in the yz plane. So again, delta x is equal to 0 in this case. And we need to focus on the other two equations, these two. We have learned that, again, we need to consider this function u of y, which depends on the, let me do it a little bit more clearer. This is the same y direction, and our function is u of y. So again, u of y, second derivative, the curvature is proportional to m, and inversely proportional to the bending stiffness, ejz. But the moment this time is different. The moment, the bending moment is given by f of y times the L of the tip, right? So it's the L of the tip, this distance, multiplied by f of y, divided by ejz. Again, we do our integration of this equation. So this becomes f of y, L of tip y, divided by ejz. And let me integrate again, and we have u of y, which is f of y, L of the tip, y over 2 ejz. If we specialize this into the L, so we want to know the u evaluated at L, we get that this is f of y, L of the tip, divided by ejz, L squared divided by 2. Okay, but again, this, I would like to recall that we introduce our c as L to the cube 3 ejz. So the trick here is to want to express everything in terms of c. So we notice that there is this quantity L squared divided by ejz. So let me rearrange the red one in this way. I do c divided by L and then multiply by 3. So I get precisely L cubed divided by ejz, which is what I want, this one. I substitute in here, and I have f of y, L of the tip, divided by 2. Yes, divided by 2. And I put 3c over L. And if I rearrange this, I have 3 over 2, L of the tip divided by L, c, f of y. So we have already obtained what we wanted, which is this coefficient, because this is c, this is delta z, f of y. So it's CZY. This is CZY. CZY. Okay? Now we want again to obtain, we solved this, we need to solve this one, so we get delta y in terms of f of y, but delta y, again, don't want to spoil it, but it's due to a rotation angle alpha. So alpha L of the tip, okay, it's our delta y. And the alpha is again obtained making use of this, the first derivative. The rotation is this one. The rotation u prime of y specialized into, so let me copy it so we avoid mistakes. Copy like this. And we specialize it, so it's u prime of L is equal to f of y, L of the tip, L divided by EJZ. And this is our alpha. We replace it into delta y is equal to, sorry, excuse me. We replace our alpha inside this equation, and we have f of y divided by EJZ. L of the tip, but there is already one, so it's square L. Now again the same trick. We need to insert our C, which is L to the cube divided by 3 EJZ. And I notice that in here I have EJZ, which is good, but we need L, so I rearrange the term here, so C over L to the cube, L square, sorry, 3, and this is L over EJZ, L, which is what I have. Let me replace it in here, so it's L of the tip squared. Instead of L over AJZ, I write 3C divided by L squared and f of y. So this is, I forgot the 2. No, there is no 2. It's 3 L of the tip square divided by L square C f of y, and this is our C y, okay? So in order to have it from a magnitude perspective, the CZZ is the biggest and the others are all smaller, okay? So the delta Z direction is so much bigger than the others. And some of them we could consider negligible, but in any case, we calculate all of them. Okay, so now, as we did earlier, we compose a little bit more this matrix, okay, because we have discovered more quantities. So first of all, we notice that CZY is equivalent to CYZ. So again is 3 over 2 L of the tip over L times C. Or maybe it's convenient to and to make it a little bit bigger. Sorry, yeah. Let me make it bigger. So it's 3 over 2 L of the tip divided by L. Let me also gather a C. So one here, this is 3 over 2 L of the tip divided by L. And this was 0, this is 0. And what else? I need CYY, which is just calculated as 3 L tip square divided by L square. Okay, because I gather up a C. And this is our, say, delta x, delta y, delta z vector, and this is f of x, f of y, and f of z. Okay, so we are populating. We are still missing 3. And let's calculate it, these 3, the last 3. These are a little bit more complicated. The reason why it's complicated is because we have as I show in a second, to consider bending and torque. Okay, because if I want to do f of x, I will get two effects. One is pure bending of the cantilever, like this. So it's a pure bending. Maybe the drawing is not the best. It's something like that. Okay, the first one is the effect of this f of x, sorry. The second one, the second effect is that there is effectively a torque, okay? So it's also torque rotating into a different angle, which we call beta. Okay, so it's just bending plus torquing. So the C total, the coefficient total that we want to calculate is due to the C of the bending plus C of the torque. But the reason being is that essentially because of f of x, again, remember that we need to extract from this to get the cxx, cyx, and czx. We need to extract, in this case, we have f of x, this is 0, so what we are extracting is this column, and the other are 0, but due to the symmetry of this strain tensor, we also can safely say that these are 0 because it's the symmetry. Okay, so essentially what we need to calculate is this C total here, C total, which is made by two contributions. One is pure bending and the other one is torque. So for the pure bending, we need to go back a little on what we did at the beginning. Where is it? Here. Okay, I take this one with me. Okay, because in this case, in the case of the bending, the JZ will be the opposite. So it's 3, okay, it's going here because it's the bending moment, but in the other direction. So it's the thickness that becomes the base and the width that becomes the height for the JZ. So what is meaning is that in our C case we get L to the cube divided by 3E. Instead of that JZ, I need to write 1 over 12 omega cube T. So this simplifies and becomes a 4. So C is equal to 4 L to the cube divided by E omega cube T. Okay. And this is our C bending. For the C torque, we need to make some consideration. The first one is that our moment, in this case, is f of x L of the tip, okay, because it's this force here times the L of the tip to get the moment. And we also introduced a beta because unlike the previous case where we used the alpha angle, in this case is L of the tip times beta, which makes the delta x that we are looking for. But again, remember that we need an equation which is essentially this one. So it's related displacement into the x direction with the forces into the x direction, and which means that we can, instead of delta x, I can use this equation here. So it's L of the tip beta is equal to, and I set this part. I want f of x, okay? So if I want f of x, I can take it from here. So let me write it here. So we have that f of x is equal to m divided by L of the tip. And so this is our C, torque m L over tip, okay? This one blue and this one yellow. So C torque is becoming L of the tip squared beta divided by m. C torque is L to the tip square beta divided by m. Okay, now is the bending moment m is very difficult to compute. Not difficult, but it takes time. I will give it to you with beta g omega t to the cube divided by 3L. So if I substitute instead of m this quantity, I have t to the torque, which is equal to beta L of the tip squared divided by beta g omega t to the cube, 3L, I put it here. This beta goes, okay. What is g? G is the shear modulus. And G appears to be proportional to the Young's modulus times 2, 1 plus nu, where nu is Poisson coefficient, which is relating the deformation into the orthogonal direction with respect to the longitudinal direction, and for most of the materials is 1/3. Okay, so the elongation in orthogonal is 1/3 the one parallel. Okay, so if you have a beam and you apply a forces, we get a displacement, a deformation, so it becomes longer but also shrinker, and this is called parallel strain because it's going in the direction of F, whereas this one is orthogonal strain because it's going opposite, it goes orthogonally to the direction of the application of the forces. So the Poisson coefficient essentially measures this ratio between the longitudinal lateral displacement of a structure subject to some forces, under some forces. So dc is E divided by 2. We said it's 1/3, so I have 3/3 plus 1/3, correct? So it's 4, 3 plus 1 is 4, times 2 is 8/3, so it's 3/8. 3/8 E. I hope I get it right. So C torque is equal to L of the tip squared, 3L, G, but G we said is A3E omega t to the cube. Okay, I can simplify this 3 and I get 8 L of the tip squared L divided by E omega t to the cube. But now I want our JZ. Okay, so omega t to the cube so I need to put inside omega t to the cube. Okay, so our JZ is 1 over 12 omega t to the cube. So 12 JZ is equal to omega t to the cube. Okay, I will put this inside here, because essentially remember that I want to express it in terms of C, and C is L to the cube divided by EJZ, because I normalize everything according to this. So what I'm doing now is to try to insert something that we can gather up as a C, a little c. So I have the numerator unchanged divided by E 12JZ. So this is equal to, I divide everything by 4, so it's 2 over 3 L over the tip square L divided by EJZ. But again, I notice that there is this L over EJZ, which I will recover from here. So it's C divided by L squared, 3, and this is L divided by EJZ. I replace this one, okay, instead of this one. So let me write it down here. So it's C torque is equal to 2 over 3 L of the tip squared 3C L squared. Okay, so 3 goes, and I have 2 L of the tip squared divided L squared C. Okay, so the C total is equal to 2 L of the tip squared divided by L squared C plus the bending one, which I don't know where. Okay, this one. Oh, I already expressed it in terms of okay. Let me think. Omega t. Yes, I also need to express this in terms of C. Sorry, otherwise it's not going to be convenient. So let me do it in here. I need to re-express this in terms of C. Okay. Okay, so C is L to the cube, 3EJZ. C bending, C bending. And 3JZ. Because if I put E, I don't want to make mistake, but it's 3C divided by 3C JZ is L to the cube divided by E. So it's 4 3CJZ divided by omega cube D. This becomes 12C 1 over 12 omega T to the cube divided by omega cube T. Sorry, but I didn't remember that I needed to express it in terms of C, so I need to correct this. T is here going, this one going, so we have 2 and 2. This one simplifies, yes, and we get C, which is multiplying T squared divided by omega squared, and therefore here we have T squared divided by omega squared C. Okay, so this is our total C. And I think we have finished, because if I take this bigger matrix here, the only one that were left were this pesky C total. So I can replace it here. Collecting, gathering up a C becomes 2L tip squared divided by L squared plus T squared divided by omega squared. Okay, so pretty much we have concluded our analysis of the inverse of the strain tensor, which is the C, and we calculated all the components. We are seeing, I can tell you that the biggest one is, of course, the CZZ. The second biggest is the CYY, and the other one, the cross transversal one, are somewhat smaller in terms of magnitude by the others. But these equations, we set of equations, discipline the displacement of our cantilever according to the forces that arises. And okay, so we can move a little bit ahead. We have introduced the fact that the cantilever is subject to the forces of the sample, as well as the sample is affected by the forces of the cantilever. So we can identify different regimes. Okay, let me put it into micron. We have different force regime. 0, 1, let's say 10, or 50, 100, let's say. I will just introduce here the regimes, and then we'll be letting discuss it during in the next video, because I'm a little bit tired. And but the point is that if the cantilever and the tip is far away from the sample, there are no forces. If the distance is higher, when it's approaching, there are forces which are electromagnetic in nature. When we get into a regime that maybe can be from 50 micron to 1 micron, this regime, we have an intermediate regime where the forces are the van der Waals forces, so related to the dipoles or induced dipoles. Whereas in the very contact regime, which is this one, the type of forces are the Hertz and the Bohr forces. Okay. Let's close it here, and we will start again in the second video from this point. Thank you very much. Bye bye.